Welcome back, guys. And now we are going to look at the last system property, which is called the linearity. So, a linear system in a continuous time or discrete time domain is a system that possesses the property of superposition. And what is this property? We are going to write the expression in a moment. So, in simple definition, if an input consists of a weighted sum of several input signals, then the output is the weighted sum of the responses to each of the input signals. So superposition, basically, uh, in superposition, we have two properties. So one of the property in a superposition is additive property, additive property, which is that if I have an input, irrespective whether it's a continuous time or discrete time domain. So if I have an input x1t and the output is y1t, and if I have another input x2t and the output of system is y2t, then the additive property says that if I add the inputs x1t plus x2t, then if a system is a linear, then the output of the system is going to be simply y1t plus y2t. So this is the additive property, which means the individual inputs, if we add them together, then the output is simply the addition of the responses of those individual inputs. The second property is called the scaling or homogeneity property. So the scaling or the homogeneity property simply states that if for x1t the output is y1t, then multiplying your input with any constant or scaling your input with any constant is going to simply result in scaling of your output signal. So a linear system is going to satisfy both of these properties. Okay. So now we can write both of these properties in a single equation, and that equation is that a system is a linear if it satisfies for this input, it gives us an output of this thing, which is essentially the same thing which I have written before, but now I have written in a simple, straightforward equation. So both the additive property and scaling homogeneity property is mentioned in this simple equation. So a linear system needs to, if you want to check whether your system is a linear or not, this is the criteria which we need to check. Another very important property of a linear system is that a linear system, for a zero input, the output is also zero. So a linear system has for the zero input, the output of a linear system is also zero. Now, if any system violates this particular property, we can say that the system is a non-linear system. Now, let's take a few examples and try to understand this thing. Okay, so the first example is, let's say the system is represented by a system equation, which is y of n is equal to 2 times x of n plus 3. Okay, so let's first check the 0 in 0 out property. So if I assume that x of n is equal to 0, then y of n comes out to be 3. Okay, so 2 times 0 is 0 and plus 3 is there. So what we can say is that for a 0 input, my output is not 0. So based upon this, I can simply say that my system is non-linear. Okay. Now please do remember this thing, that this particular condition is we check this particular condition, and if 0 in is not equal to 0 out, then we can only say that the system is non-linear. If the result would have been xn is equal to 0 and yn is 0 as well, this is not a surety that your system is going to be linear now. We still need to check it. So this is a criteria for establishing the non-linearity only. Okay, so let's say I didn't want it to use the 0 in 0 out property and I want to check it. So let's try to do that now. So let's assume an input x1n. Then for this input, remember your system equation is this one. This is your system equation, okay? So for input x1n, my output y1n is simply 2 times x1n plus 3. Let's take another input, which is x2n, and now my output represented by y2n is simply 2 times x2n plus 3. So I'm using this equation. So instead of xn, we have x1n and x2n. And now let's assume that we have another input, x3n, and this input is the sum of x1n and x2n. And now let's try to find out the output of a system in response to x3n. So x3n is going to result in an output represented by y3n, and this is going to be equal to 2 times x3n plus 3. So what we have done is we have referred to this original system equation. And now instead of x3n, I can write x1n plus x2n plus 3. So now if I open it up, this is 2 times x1n, 2 times x2n plus 3. So this particular thing, which we have calculated over here, is now not equal to y1n plus y2n. Because y1n is 2x1n plus 3, y2n is 2x2n plus 3. So in order to have equality over here, the term should have been 2x1n plus 2x2n plus 6, which is not the case. So what happened over here is that when the input is sum of the individual inputs, when the input was x1n plus x2n, the output was not equal to y1n plus y2n, which means that my system is non-linear. The same result which we have already proven by using the 0 in and 0 out property. Okay, so let's take another example to check another case. So the second example is, let's say my system is represented with this equation, t times xt. All right. Now, again, what we can do is we can check the 0 in and 0 out property. And if you apply the 0 in 0 out property, what you can see is if x of t is 0, then y of t is also equal to 0. Now, please note that doesn't mean that the system is linear. I still need to check completely. Okay, so I still need to check. So let's check the uh, system now. So for x1t, my output is y1t is simply t times x1t. So remember, this is the original equation, system equation. And then for x2t, the second input, my output is going to be y2t equal to t times x2t. Okay. And then we are going to assume a third input, x3t, which we are going to say that it's a sum of these two inputs. And then let's find out that what's the response of the system to x3t. So x3t is going to give me y3t as an output, which is equal to t times x3t. So remember, this is the original system equation. So y3t, t times x3t. And then we can substitute, instead of x3t over here, x1t plus x2t. And if I open this bracket, then this is t time x1t plus t times x2t. And if you look closely now, this t times x1t is basically over here y1t. So this term is y1t, and this term t times x2t is y2t. So what we found over here now, that when the input is the sum of the individual inputs x1t and x2t, the output y3t is the sum of the individual outputs y1t and y2t. So now this proves that my system is a linear system. Okay, so this is a proof of a linear system. So let's take one final example to conclude this part now. So let's take another example. So let's say my system is represented with this system equation. So now if I again check my 0 in and 0 out property, so if x of t is equal to 0, y of t is also equal to 0. Now again, it is important to understand this thing, that this doesn't imply that my system is going to be linear. I still need to check. The violation of this confirms that the system is not linear. But if it's satisfied, that doesn't mean that the system is linear. We still need to check. So let's check. So for x1t, just like before, we are going to have y1t that is equal to x1 square t. Then for a second input, x2t, my output is y2t x2 square t. Remember, this is the original system equation. And then, just like before, we are going to assume a third input, x3t, which is a sum of these two inputs, x1t and x2t. And let's find out the response y3t in response to this, the system response in response to x3t. So when x3t is an input, y3t, the output is simply x3t square. Okay, I could have written the square over here as well, that is fine. But I have intentionally mentioned it over here to make things a bit clearer. Okay, so now substitute the, instead of x3t, this particular relation. So what we have is x1t plus x2t, and it's a square now. And if I open it up, I'm going to get x1 square t plus x2 square t, and then there is going to be a third term, which is 2 x1t x2t. Okay, it's a formula of a plus b square. And now what we can see is that this is not equal to y1t plus y2t, because y1t was x1 square t and y2t is x squared 2t. So this particular term is an extra term, which makes it not equal to y1t plus y2t. So now the system is non-linear system, because when the input was the sum of the individual inputs, the output y3t was not equal to the sum of the individual outputs. So it's a nonlinear system. So it's important to realize that although it satisfied the zero in and zero out property, the system is still a non-linear system. So the zero in and zero out property, you are going to use it to establish only the non-linearity. So if the zero in and zero out property is not true, you can say with a confidence that the system is non-linear. But if the zero in and zero out property holds true, that doesn't mean that the system is going to be a linear. You still need to check it. For example, here we check it, it's a linear system. It satisfied the zero in and zero out property like over here. But in the second case, although it satisfied the zero in and zero out property, the system was the non-linear system. So with this, we have concluded the system properties. Just one last comment. The two very important properties of the system are basically the linearity and the time invariance. Why? It's going to become evident in the chapter number 2 that the systems which are linear and time invariant are one of the most important systems. Those systems are called LTI systems, which is LTI systems. So these are the systems which are linear and time invariant systems. And we have now studied both of these properties. And in chapter number 2, we are going to see that the LTI systems, the output of an LTI system can be computed very easily in a straightforward manner. And most of the systems which we encounter are actually linear and time invariant systems. So in chapter number 2, it's going to become evident why the LTI systems are the most critical or important systems when it comes to the signals and systems course. Thank you. Bye-bye.